A solution, I'm happy with that. In the first step, I have to change the equation into this. Why? Because I have to denote this by f of x. That's our first step. So I know that this is a continuous function. So by IVT, right, f of x I see is continuous. I have to find the interval on which the function changes sign. I will have to use a calculator for that. And you can say, fine, so if you determine where the solution is, why don't you just punch it in the calculator and get the solution? True. But we need to illustrate Newton's method, so you understand how brilliant this is. I find it very interesting. Okay, so I will put this in the calculator, and I will find an interval, a 1 unit interval, where the function has a solution, or where the function has a 0 or an x-intercept. At the same time, I will find on the side f prime, which is cosine x minus 2x. And that's the next step. So in the calculator, please punch in this function in y equals, clear, clear. Okay, so sine x, make sure your mode is in radian mode, minus x squared, and plus 2. And then I go to second table, and I will start by plugging in 0 and 1 and 2, and I'm happy. I found that at f of 1, make sure that radians, yes. I found that I know that the function is continuous as a sum or difference of continuous functions. So I found that if f of 1 is positive and an f of 2 is negative. That's good enough for me. 1 and 2, f of 1 is positive, f of 2 is negative. By IVT, I will find a c in the open interval 1, 2, such that f of c is 0. Now Newton's method will find it for us. Okay. Then I will write Newton's method and create a function. I'm going to call it uppercase f of x. I don't want it to be confused with antiderivatives. So let me choose a different letter. Newton's method. Newton's function. Because we use this in chapter 5, and this is very important. So I don't want you to get confused with this. So I changed the name. It's the Newton's method, Newton's function. And Newton's function is x that I choose to start with minus f of x over f prime of x. I will replace the function. I didn't want it up there. Minus f of x, which is sine x minus x squared plus 2, divided by f prime, which is cosine x minus 2x. This is our Newton's function. And this is the function I will enter in the calculator. Do not delete what you have, because we're going to use it right now. So go back to y equals, and insert x, second and insert. No, not there. Second and insert. And I have x, and then minus, put a parenthesis, because you have to put the numerator, entire numerator in parentheses, divide in parentheses by cosine x, close for the cosine x, and then minus 2x, and close the parenthesis for the denominator. Should I wait? Do we all have this already? Do we have this plugged in? Is that a yes?
Yes.
Okay, good. So now I will continue with second and quit. Clear? We have to decide where we want to start. If you want to start at 1 or if you want to start at 2, there is no problem. This cosine 1 radian minus 2 or cosine 2 radians minus 4, it's not going to be 0. So there is no problem. We either start at 1 or start at 2. It is possible, however, that if we start at 1, we get the solution with 8 decimal digits in 3 steps. And if we start at 2, we may get it in 4 steps. It doesn't really matter. It's not a big deal. So which one will be x sub 0 for us? And we have to write it down. 1 or 2?
1.
1 it is. So in the graphing calculator, we will do this. We will go to variables. Variables. We will go across to y, variables. We will click on function. I want to call function y1, and I want to plug in 1. So this is function y1. I plug in 1, and I press enter. What do you think this is? 2.26154271. Will anyone give it a shot? What do you think it is? Of course, it's x sub 1, our first iteration. You could say, aren't you a little bit concerned? Because the solution is between 1 and 2, and look what you got. I am a little bit concerned, but I'm going to give it a little bit of time. So now I recall what I had before with second and entry. I overwrite 1 by the previous answer. So now in Newton's function, the calculator will insert this value. And in the next few steps, if I do not get closer and closer to a number between 1 and 2, I will say to myself, uh-oh, something is wrong. So let's see what we get for x sub 3. I feel much better. F sub 2. X sub 2 is 1.807334422. Now I don't have to do anything, just recall. And the calculator automatically will insert 1.8. Aha, I'm happy. X sub 3 is 1.73087246. I repeat, x sub 4, 1.7284688707. How many times do I do this? Oh, you'll see in a moment. Do I have 8 repeating digits? 2, 4, 6. I don't. So x sub 5, 1.728466319. If the next one is completely the same or the first 8 digits are the same, I'll stop. And it's absolutely the same. So this is it. I don't have to move on. So the method converged in 1, 2, 3, 4, 5 steps. So in 5 steps, we obtained a solution that we would have never dreamt of finding. Literally. It cannot be done by hand. And you can say, but you haven't done it by hand. True, I haven't because the calculations are cumbersome, but I could have done it by hand. But there is no algebraic method that solves this. And this is Newton's method. Question, do we need another example? If you say yes, please choose another example. If you say no, I am finished with Newton's method, I'll go back to optimization.
Can we see another example?
Yes. Very good. So let's find another example. Okay, here's an example, an application basically. It says, use Newton's method to approximate the given number correct to 8 decimal places. So 8 decimal places again. And they want us to approximate the 5th root of 20 using Newton's method. What is that? How will I even start approximate? What is the function? I can't use Newton's method if I don't have a function. What is this? Okay, so here's the idea. X to the 5th minus 20 equals 0. Why? Because x to the 5th equals 20, and I apply the 5th root to both sides, and I get x equals the 5th root of 20. So in order to approximate something like this, I need this function. Of course, you can say, but it's an equation. Yes, I need to have an equation that I'm trying to solve. So the function is this. So I can approximate that by solving this equation using Newton's method, because if without a function, without a derivative, without a starting point, I don't know what to do. Okay? So if I'm asked to approximate that, I have to start with this. So then our function is f of x equals x to the 5th minus 20. I will immediately find f prime of x, which will be 5x to the 4th. I will create my n of x, which is x minus the function x to the 5th minus 20 over 5x to the 4th. I need to find an a comma b. This is a continuous function, f of x continuous, but I have to see where it changes sign. I use the graphing calculator. So 20, you can say, but you are already approximating it now. Yes, but not with Newton's method. I just need to see, it's somewhere between 1 and 2. That's all I needed, because I need to start somewhere. So the interval again is 1, 2. You tell me where you want to start, and that's our starting point. And then we continue with x1 and then x2 till we get a repeat of 8 decimal places. And this is how we use Newton's method to approximate anything. So in y equals, please tell me what you would like to start with. And I will enter x minus parentheses for the top, x to the 5th power, and then minus 20. Close the parenthesis and divide. It has to be in parentheses, 5x to the 4th, although it's a one term, because otherwise the calculator will divide by 5 but multiply by x to the 4th. So 5x to the 4th power. Okay. So tell me I already have Newton's method, Newton's function in there. So now I want to go to second, and I meant to quit. Okay, so variables, function 1. I'm waiting for your x sub 0, either 1 or 2.
Let's use 2.
Okay. It may converge faster if we choose 2, because we found the solution was roughly 1.8. Good. So I plug in 2. I get 1.85 is the first iteration. Better the approximation than 2. And now I repeat, but I replace 2 with the second answer. Second and answer is the previous, it recalls the previous answer, and I press enter, and I get 1.82, 1.486, 137. I repeat, I don't have to write anything. X sub 3, 1.82, 0, 5, 6, 5, 136. And x sub 4, do they repeat 6 of them? 24, nope, not yet, 1.820564203. Probably the last one is that one. Yeah, that's it. So it converged in 4 steps. And this is the approximation of the 5th root of 20. You never thought that you could take the 5th root of 20. Now you can. Using calculus, you can approximate any number you want without having to take the 5th root per se. Okay, anything else? Do we need another example, or did we get the idea? Oh, I forgot to mention, of course, it doesn't matter 1 or 2. The denominator is not 0, and the derivative is not undefined. Anything else? Do we need other examples, or now we focus on optimization?